Hi there, how are you? I am thinking about using a phrase that I heard on TikTok that I like, although it has nothing to do with my classes or these topics. Have a nice cooking, good looking. Well, you can say that we are cooking algorithms. Okay, so today I will talk a little bit about an example that comes actually from the greedy type of algorithms, and it is a very nice algorithm that you may find everywhere, at least to study. And remember that the greedy approach or the greedy methodology to solve problems is based on this idea. We will be expanding a solution that has been partially constructed, adding at each step a new element to the solution until the complete solution is reached. And this implies, of course, this iteration, and the iteration needs, of course, a choice to be made. But this choice has to accomplish several things. First, it has to be feasible. Usually, in the optimization problems, we have constraints that we need to respect. So we will say that the solution is feasible if it satisfies the problem's constraints. Also, the solution that we are choosing has to be locally optimal, meaning that at each iteration, each step, we will need to choose the best we can do at that moment. This is a local best from, of course, the feasible alternatives that we have to choose. And finally, it is irrevocable. It means that in this type of algorithms, once we make a decision, we cannot change it. We will have to live with that decision further in the construction of the solution. And with that, we can start talking about a nice algorithm that is used in order to compute what is called the Huffman codes. And the idea is the following. We want to encode a message that is composed by a string of characters. And usually when we store a text file in our computers, depending on how old they are, but in any case, they need to use some codes in order to represent the characters. The two most well-known codes for doing that are the ASCII code and the Unicode. The difference between them is the amount of memory they use. ASCII codes use 8 bits per character, which means that they can encode, by using this encoding system, we can encode 256 characters. And Unicode uses 16 bits per character, which of course can lead to the possibility of encoding up to 65,000 characters, which includes, of course, all the ASCII characters plus new ones, which are important, for instance, when representing characters in languages that require accents and characters, more characters. Both ASCII and Unicode are fixed length codes, which means that every character we choose requires exactly the same amount of bits. So in the case of ASCII, we use 8 bits, and in the case of Unicode, we use 16 bits. However, there are also another possibility. There is another possibility, which is to use variable length codes. So instead of having fixed length, we may consider the case where the characters use different lengths. So in this case, if we were to use something like this, a logical decision would be, if we have characters that happen more frequently in the text, I will assign shorter encodings to them to save space, and the ones that appear less times in the text, they can be a little bit longer. So what we want is that by doing this, we would like that on average, the length of the encoded message is less than the fixed length encoding. This meaning the ASCII or Unicode. So, however, the main issue here is how do we know where one of the character ends and the other character begins? Because in the case, of course, when the bits, the number of bits is fixed, we know that this is not a problem. I will read the first 8 bits and that will translate into the first character, considering ASCII. Then the next 8 bits will be the next character and so on. But if the length is variable, then this is going to be different, right? So in the diagram here that move a little bit when I imported to this app, we can see, for instance, a string of the binary string representing the characters, and we want to translate it to the alphanumeric thing. So we have on the left side the encoding for the different characters. So let's suppose that A is encoded by 00, B is encoded by 01, C by 10, and D for 11. So it's a 2-bit encoding. And by doing this, I can basically separate here in twos and so on, and then translate that. So this 00 corresponds to A, 10 corresponds to C, 11 corresponds to D, 01 corresponds to B, 11 again to D, and so on, which is actually what is written here. So in this case, I basically just take the string and separate the string considering the bits that are needed in order to represent the character. So I can go from the, well, of course I can go both ways, but in this case I have the binary string to convert it to characters. But how can I manage the possibility of using variable length codes? Well, first we need to talk a little bit about something that is called the prefix property. And we say that a code has the prefix property if no character code is the prefix or the start for another character. So let's take a look at the table that we have here. We have the symbols P, Q, R, S, and T, and we have assigned the codes which are on the right. They are of variable length. You can see that there are some with length 3, and there are some others with length 2. So P is represented by 000, Q by 11, R by 01, S 001, and T 10. And we have a binary string on the right of the table. And we can translate that into the characters which are below. And the reason is that I can start reading the string, the binary string, and then I see, well, 0 is the start of P, of R, and S. So it could be, up to this moment, it could be any of those. I still don't know. So I move to the next one, and it's 1. So this one is already discarded. And this is going to be the good one. 01 corresponds to R. So that is why we have the R here. So we have eliminated these two guys. And then the process starts again. Let me clean here. And the process starts with the next 0, same story as before, and then 0. So up to this point, let me clean. Up to this point, 0, 1. This is not 0, 1. I'm sorry. 0, 1. And cannot be, you see? So at this moment, 0, 0. Oh, I'm sorry, I read it incorrectly. Let me clean. Yeah, I didn't notice. Okay, that's better. Okay, so we were saying 0 and then 0. So could be this or could be this. And then a 1. So 0, 0, 1 is this. This cannot. So the next character is going to be the S that is here. And then I have covered all these characters and we can move. We can move forward. So again, we start with 1, and this one may imply this one or this one. Then I move to the next one, which is a 0. So I discard this one, and I know that is going to be the T, which is here. You see? So it's going to be the T. And so on. So we can continue this process and we will translate in only one way. There is no way that we can make a mistake and I translate this string to be RSTQPT and somebody else gets something different. And the reason for that to happen is that we can notice immediately that, for instance, 000 is not a prefix of any of the other encodings. It doesn't happen at the beginning of any of the others, as well as 11 is not a prefix of any of the other, and so on. So, no character code is a prefix for another character. So this way of encoding will guarantee that when translating, we will achieve the same unambiguously translation. Okay, so it's a nice property. However, of course, the question now would be, how do we decide to assign 000 to the P, 1 to the Q, and so actually it doesn't really matter the mapping, as long as the prefix property holds. But of course, from the practical point of view of not just encoding, but also doing it in an optimal way, the way we assign those codes is going to be important. So let me clear. And then, in order to do that, there is a way of assigning these codes that is called the Huffman encoding. Huffman coding at the end is a lossless data compression algorithm. We will not lose any information by doing this, and we will save space. The idea of Huffman encoding is to assign variable length codes to the characters that we are wanting to represent. But the length of these codes is going to be based on the frequencies of the corresponding characters. So the shortest ones, the shortest codes should be assigned to the characters that appear more frequently. In that way, we will save more space. And of course, the least frequent character is gonna get the largest code. the way to build the Huffman encoding is through a Huffman tree. So the process is very simple. The first thing we need to do is to count or compute the frequencies of each one of the characters or symbols appearing on the message. Once we have this information, we will begin with a forest composed of as many nodes or trees as symbols we have in our message. And we will also preserve the value of the frequencies of each character along with the character itself in the same node. And then recursively, what we are going to do is that we are going to select the two trees with the smallest frequency and join them with to form a new binary tree. The root node of this binary tree is going to contain the sum of the frequencies of the two children. And we will continue with this process until we have only one tree. And this is going to be actually the Huffman coding tree. And we will use it to get the codes. We'll see. So let's suppose that we want to encode using Huffman codes a very simple message that is, this is his message. Okay, this is what we want to encode to illustrate the process. So what I will do is I will compute the frequencies of each one of the characters that appear on the message. So I have a T, I have an H, I have an I have an S, I have an E, an M, a G, and I believe that's all. The blank too. So what you see in this table is the characters and the corresponding frequencies. How many times they appear, basically. So the A appears only once, the G appears only once, let's see another one that happens more than once, the E is here and is there, so that is why we have the 2, and so on. So with this information, we can create our forest. This forest contains, as we said before, as many trees as characters or symbols we have in the message. So we have one node for each one of the characters, and inside we are storing the frequencies. And then what we need to do is that we choose the two trees with the smallest frequencies. And you can see here that we have several options. We can take, for instance, A and G, or we could take G and M, or M and T, or A and M, or because in this case we have several cases with the same value of the frequency. It doesn't really matter for now. Let's suppose that I decide to join A and G in a new binary tree, and this tree, of course, has frequency that is the sum of the frequencies of the other two elements that were integrated. And now we have this forest. At this moment, we will join these two in order to do something like this. And now we have several tools, so we could, for instance, let's see, we could join let's say that these two here, and then we can do this two And now we have fours, we have threes, and now we can, this is a 5, so we have two fours here, and let's join them, 8, and the smallest now are the 6 and the 5, and they will give 11. And then, of course, at the end, we only have the option of joining these two guys in 19. All right. So this is the trick, because now we only have a trick. We have to stop, and the way in which we generate the encoding is the following: we will assign a 0 to the left branches and a 1 to the right branches. So 0, 0, 0, 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1, 1, 1, and 1. So you can imagine, let's suppose that I need to get the code for the E. In order to go to the E, I will need to follow this path, which means E is gonna be 0, 1, 0. And we can choose another one. Let's suppose that the M. At the end, I will have to do for all, right? But for the M, we will follow this path here, 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 which means 0, 0, 1, 0. And let's do one more, the I. I will follow this path, which implies 1 here, 0, 1. So you can see that we have a variable length. We at least know that we have some elements with 3 bits, and some others with 4. And if we go back to the table of frequencies, we can notice, for instance, that S is the character that appears more times in this message, with 5 occurrences. So let's see what happens with the S. Let's do it here. In order to go to the S, we will go 1 and 1. So it's 2 length. And the next one was with 3, both I and the blank. We already have the 3. So it means that in this case, there is 1 character to represent, I'm sorry, 2 bits to represent the S, 3 bits to represent the I, and probably M is one of the characters that appear less times, and only appears once, as well as T, G, and A. So this shows that this is happening. I mean, we are using shorter code lengths for the characters that appear most frequently. And this is in a clean way what I was doing, and we can get a whole table like this one. So if you see, we could translate the message that is below as a binary string again back to the characters by using these codes. So for instance, I start reading 0, then 0, still none, 1, 0, 0, 1, and none of them is there. 1, 0, 0, 1 is T, 0, 0, 1. So up to here is the first character. Then we start reading the rest. 0, 1, 0, 1, and 0, 1, 1. It's 0, 1, 1 is this one. And then 0, 0, 1, 1. Then 1, 0, 1. 1, 0, 1 is an I. And so on. So if you complete this, you will end up with the original message, of course. I recommend you to do it, although it will take a little bit of time to make sure that this works. And in this way, we can generate encoding a scheme that optimizes the number of zeros and ones needed in order to represent a message like this one. I hope you enjoy.